This animation describes the process of determining strain-pull figures from finite element simulations. Here is the tension specimen that we will model. We zoom into the metal, increasing resolution to examine its microstructure. In this specimen, at about 1/10 of a millimeter, separate grains become evident. Looking at about 3,500 square micrometers of the sample, two metallic phases are visible as light and dark regions. Each phase is comprised of crystal grains of differing crystal lattice orientations, shown here for both of the two phases by different colors. A closer look at two such grains reveals their lattice orientation. In the finite element simulations, we retain the lattice orientation, but approximate the grain shape as dodecahedra. The volume of metal examined in every simulation is thus represented as a cube of dodecahedra, each representing a grain of metal. Again, the color of each dodecahedron displays the lattice orientation of that grain. Now the color scheme is altered to identify in red those crystals that light up in a diffraction experiment. Lit up crystal grains, that is, grains with lattice orientation satisfying a particular Bragg condition, are isolated in the volume. In this case, all crystals having 100 planes perpendicular to the Z sample axis light up and are colored red. A closer look at each grain reveals the lattice structure. Note that the lattice orientations differ by only a rotation about the Z axis. To help interpret simulation results, we wish to plot each crystal strain as a function of its lattice orientation. The Rodriguez box is a three-dimensional orientation space that helps to visualize the orientation of the crystal lattices of simulated grains. Every point in the box corresponds to an angle axis vector associated with the unique orientation. The magnitude of the Rodriguez vector, salmon color, determines the rotation that the crystal experiences, around the direction of the vector to take it from a reference orientation to its own orientation. The crystal is represented in the Rodriguez box by using the Rodriguez vector, starting from the box's origin and pointing to a unique position inside the box. Rotating around a single axial vector shows the symmetry of the FCC unit cell. For a cubic crystal, a 45-degree rotation about a 100 axis is equivalent to one of -45 degrees. We start with the crystal and sample axes aligned and rotate it about the sample Z axis, which is the crystal 100 axis. When the vector reaches the box boundary after a positive 45-degree rotation, we reposition it to its symmetrically equivalent point at -45 degrees of rotation. Rotating by 45 more degrees brings the FCC unit cell back to the starting point. The Rodriguez vector thus returns to the origin of the Rodriguez box. The orientations of crystals lit up earlier are now mapped to the Rodriguez box as shown. Note that all of the vectors are parallel to the Z-axis. This clearly illustrates how the orientations of all the lit crystals are related to each other. That is, they share the same orientation axis, and they differ in orientation only by the amount of rotation about that axis. The result is a set of points in the Rodriguez box lying on a line or fiber, and representing the orientations of all lit crystals that satisfy one particular Bragg condition. Now we're ready to superimpose data for the elastic strains. On top of the points representing lattice orientations, jacks are plotted. Jacks represent the lattice strain's principal values and directions, or eigenvalues and eigenvectors, at each of these grains. The sample is now put into tension and stretched by about 30%. The simulated volume also stretches, as is evident from the changing shape of the grains. The deformations are predominantly plastic, occurring by crystallographic slip. As part of the slip process, the lattice rotates. It also distorts elastically, as shown here in a highly exaggerated manner. The distortion of the lattice can be detected experimentally by using diffraction methods. A displacement of one plane relative to another in a constant wavelength radiation diffraction experiment causes a change in the angle between the inbound and outbound beam, as given by the Bragg condition. A common practice is to measure the change in this angle to derive the change of separation between parallel planes, and in turn, to derive the elastic strain in the direction bisecting the inbound and outbound ray, in this case, the tension direction. Again, the lit up crystals for one diffraction condition are isolated and are represented inside a Rodriguez box at the points corresponding to lattice orientation. Principal lattice strains are calculated from the simulation results and are plotted as jacks at the corresponding orientation. The cycle repeats for many directions in the sample. The jacks on the Rodriguez figure show lattice strains for crystals having a 001 crystal direction aligned with the sample z-axis. Again, color of each leg indicates the magnitude of the principal strain value and the orientation of the leg indicates its direction. Individual jacks correspond to strain in individual crystals. The diffraction volume often contains many crystals, so the measurement contains contributions from all crystals that light up. For all the jacks along one fiber in which the crystal 100 axis aligns with the sample z-axis, we calculate the z-strain components and take their sum. The values are then averaged, and the resulting strain is indicated here by a color of a line that extends over the complete fiber. The average strain value is then plotted as a dot on the strain pole figure by finding the intersections between this line and the unit sphere. A dot's color represents the average normal component of the lattice strain in a direction normal to the unit sphere at the location of the dot. The crystals on the fiber defined by having a crystal 100 axis parallel to the sample x-axis are now identified, and the value of the normal components of the lattice strain in this direction are calculated following the same procedure used before for the z-direction scattering vector. The calculated value of strain in the x direction is now transferred to the pole figure as color-coded dots on the surface of the sphere. Next, the jacks corresponding to crystals having a 100 direction aligned with the sample y-axis are identified. The average value of strain in this direction is calculated, and the value is transferred to the pole figure. Similarly, the average lattice strain values along many other fibers' directions are computed and plotted on the pole figure. In this situation, other strain value points on the sphere's surface are determined from z-axis symmetry, and the figure is completed. Other strain pole figures are determined in a similar fashion. Using these, it is possible to graphically display the average strains that the specimen endures in any direction when loaded.